Hi everyone, my name is Tommy and I'm a senior software engineer here at Labelbox. In today's video, I want to educate you some more on the concept of embeddings within machine learning. To do so, we'll first go over some of the theoretical background, which is filled with some of the practical examples to get you a better sense on what are embeddings, what are they used for, what do they measure, and how are they generated. However, at the very end, we will also take a look at Labelbox platform and go over some of the products that are being powered by the concept of embeddings. So let's first kick off with a definition of what an embedding is. Embedding is a vector representation of an information in a compressed format. That information can be of any modality. It can be video, audio, it can be text. It really depends on the underlying compression algorithm, or better to say, a deep learning model, and what was it trained on. Each index in a vector is a numerical value. We have a sample vector representation over here where we can see the first 5 values. Those values are floating point values on scale 0 to 1. Each of those values, in a way, embody, or better to say, embed the information from the input asset. For example, let's say we have an image on the input. The underlying compression algorithm would convert that image into a vector representation, preserving all of the relevant information. Embeddings can be then used to determine similarity between the two assets. So for example, let's say we have an image with a cat on it and another image with a dog on it. Because those are separate entities, cat and a dog, the similarity score between those two embeddings, between those two assets, would not be as high. And such similarity is actually computed by similarity algorithms, one of which being the most popular one, cosine similarity. It's also worthwhile mentioning that dimensions of a vector describe the level of detail. The higher the dimensionality, the higher the detail, but also accuracy and confidence in the similarity score that you get. You can imagine if your vector representation only contains 2 values or 2 dimensions, it's highly unlikely that those 2 dimensions would be sufficient to store all of the relevant information. On this slide, we have examples of how images are being converted into vector representations. Let's imagine that the underlying model, which is used to embed these images, was trained on a dataset containing images of helicopters, planes, and humans. Obviously, this model will be good at recognizing those 3 entities, but no other. On the first image, we can clearly see that there is a helicopter being present. So that being said, the vector representation would be 1, 0, 0. On the second image, we can see that there is a helicopter, but we also see humans being present on it. So the vector representation would be 1, 0, 1. The third image is an image of a tree, which does not fall into any of our 3 classes that our underlying model was trained on. So the vector representation would be 0, 0, 0. Even though that this is just a basic example, it might give you a better understanding of how embeddings are being generated. Due to the nature of vector representation, embeddings are extremely suitable for search problems, especially within recommender systems. So just some of the applications of embeddings within the search applications could be, well, you might have an image of a dog and you want to find all other images that are similar to your image, or you would actually expect that those images would contain a dog. So that's where embeddings come very, very useful along with the proper similarity algorithm. Or another use case could be that you don't even have an image, the input image. You just have a textual query. You have, you just want to, you provide a prompt, you provide a query which is image of a dog. And that can be also used in the same manner, in the same way to find all other images, all images that resemble your input query. There are definitely some more advanced, some more complex use cases where embeddings come also super handy. So for instance, let's say that I want to learn more about some topic. Let's say that topic is machine learning. I could simply have an application which will find all the relevant articles that speak about the topic that I'm interested in. So It serves as a search engine. And I guess one last example that I have here is, let's say that I love watching movies and I keep track of all of the movies that I've watched and I keep rating them just so I know the ones that I enjoyed watching. And embeddings could be used here to find all other movies that are similar to the movies that I watched before, that I enjoyed, that I rated highly. The search engine could propose to me, hey, this is the next movie you want to watch. So yeah, it's a recommendation for you. So yeah, there's like a handful of use cases where embeddings can be certainly very helpful. So let's talk a little bit more about how we can measure similarity between two assets. The most popular algorithm for measuring similarity between two assets or two vector representation is cosine similarity. It's not the only measure, it's not the only algorithm. There's more, but it's one of the most frequent ones. The idea is that when you have two vectors that are within the same dimensionality, the angle between the two kind of like indicates their similarity. So the smaller the angle, the more similar they are. And on the other hand, the larger the angle, the less similar they are. And the similarity score is actually represented on a scale 0 to 1. You can also actually find the scale -1 to 1 if you want to measure how dissimilar they are. So let's just quickly jump onto this figure over here, where we can see the graph on a first the first graph. We see those two vectors W and V are very close to each other, and their cosine similarity measure gives us actually a value of 79% or 0.79. On the other hand, we see that third graph where we W and V vectors are actually opposite one another. So they're not similar, they're dissimilar actually. And if we put this into the context of movies, let's say that I enjoyed watching movie W, represented with the vector W. I'm most certainly not interested in vector V, because it's something that does not very well represent what vector W is. So yeah, this is kind of like to visually give you an idea of how the cosine similarity measure is computed. And now to go back, I just want to mention a little bit more about some of the problems with similarity computation. There are the three characteristics that I have mentioned here. There's definitely more. So one of those characteristics is the latency. So the similarity computation is not super easy computation, but it's not so much about how quick it is. It's more about the volume across the assets that you're doing it. Another thing to keep in mind is also that you do need, if you're doing similarity computation across lots of assets, you do require some high computational resources. And the last thing is accuracy. In some cases, similarity results we get from the similarity algorithms might be very accurate, but in some cases they might not be. So those are kind of like the problems. There are some of the characteristics that you want to account for when choosing the right strategy for conducting your similarity computation. So there are definitely much more strategies than the ones that I have listed here. Those two can be broken down even further. I just keep them on a high level to kind of like help you better distinguish what are the pros and cons of each and how they account for these problems and kind of like the characteristics that I mentioned previously. So one of the strategies to similarity computation is doing the brute force search. So, which essentially means that you are comparing one asset against every other, so that you can see how that one asset compares in measure of similarity score to all other assets you have. So this will provide the highest accuracy, simply because you will be essentially comparing your asset against every other. But this requires lots of computational resources, and this could lead to higher latency. So you can imagine if you need to do this operation across 1 million assets, it's going to be pretty slow, and it's going to require a lot of computational resources. The other thing, kind of like the other strategy, which again has some pros and cons. It's up to you to decide to make the trade-offs. But it's kind of like smart similarity, usually powered by different variations of approximate nearest neighbors. And this one provides high accuracy, may not be as high as brute force, but this strategy significantly lowers down the computational resources and also latency. The way how usually those algorithms works is that they do not check one asset against every, but they just try to approximate a number of assets that should be tested, or against which your input assets should be compared to. So you can imagine that with ANN strategy, with smart similarity strategy, you might be actually comparing your one asset against 100,000 assets, and not like 1 million, as it would be the case with, let's say, brute force approach. And lastly, let's just briefly talk a little bit more about generating embeddings. Deep learning models trained on a generalized or subject-specific dataset learn patterns from data, which enables them to identify shapes and more complex objects. Depending on whether your model was trained on a specific dataset or more generalized dataset, you will be provided with different types of capabilities. For instance, if your model was trained on a specific dataset, let's say cats dataset, your model will be likely very good at identifying different breeds of cats. However, it will not be good at identifying any of dogs. So that's where generalized model might be more suitable. Because generalized model was likely trained across different type of entities and domains, and that being said, the model has capability of identifying all those entities. Once such model is trained, you may provide it with an asset, depending on the modality it supports, and it will generate a vector representation for you. Nowadays, models usually produce embeddings with over 1024 dimensions, which increases the accuracy and the detail of the vector representations. However, this also brings some challenges, such as cost of the embedding generation, cost of storage, but also computational resources that are needed to compute similarity. And before we wrap up, let me show you how some of the products and Labelbox platform utilize embeddings to improve the search capabilities. Here we are within catalog product of Labelbox platform, which offers several similarity search capabilities. And the first thing that we're going to try out is finding all images that are similar to our input image. I'm pretty curious to see what are the images that we're going to get as a result when looking for the similar ones compared to this image where we have 3 basketball players on a court. To do so, I'm just going to click on the button in the top right corner. Under the hood, Labelbox executed a similarity search on our dataset. And here are the results that we got. You can see that those results are pretty awesome. All of them actually have basketball players on a court. The second similarity search functionality we want to explore is called natural language search. Here, in the filters dropdown, we can select natural language filter. This functionality allows us to search our assets, in this case images, by providing a query in a textual format. So let's see what results do we get when we type in dog. We can see we got some pretty good results. Dogs are in one way or another appearing in most of the images. To make sure we remove any noise, we can always increase the target similarity score. That is all from me for today's video. Hopefully your understanding of embeddings and what are they being used for is now a little bit clearer. Thank you.